Hello everyone, my name is Yu Wei. I'm currently a PhD student at Purdue University. Today I'm going to present our work, Eureka, a general framework for black box differential privacy estimators. This is a joint work with Yun from University of Victoria, Malik from Rensselaer Polytech Institute, and my advisors, Vasilis, who is also from Purdue University. So our work are motivated by the following scenario. We have a domain expert who knows quite well how to extract useful information from a dataset, but he might not know how to show the extracted information preserves strong data privacy. Let's imagine that the domain expert designing a machine learning algorithm M. So here we call it mechanism M. The mechanism M might already use some randomization techniques to improve efficiency, and the domain expert might already heuristically add some noise in the mechanism M. Then, how private the mechanism M is, because intuitively it has some randomness, internal randomness, and then the mechanism's output distributions have some uncertainty. We would like to help the domain experts answer such question in a black box way. This is because if we could answer it in a black box way, then the domain expert can empirically estimate the privacy of its mechanisms by themselves. So when we talk about privacy, we refer to the standard privacy notions, differential privacy. DP is the property of a mechanism. Intuitively, a mechanism is epsilon delta dp if for all neighboring inputs in its domain, the corresponding neighboring output distribution shall be epsilon delta closed. So what does epsilon delta closed here mean? It's formally captured by the inequalities shown in the slide. Then a formal way to rate dp is that there is no algorithm A with probability at least 1 minus delta for whichever neighboring input it chooses. The algorithm A cannot distinguish the neighboring output distributions with advantage more than epsilon. So we propose the notion called a privacy spectrum to capture all the most interesting and incomparable epsilon delta pair that a mechanism satisfies. So recall that a mechanism might satisfy different epsilon delta pairs. And some epsilon delta pairs are not that interesting. Say every mechanism truly holds any epsilon larger than or equal to 0 and delta equal to 1. This is not interesting. And some epsilon delta pair are not incomparable. Say a mechanism satisfies epsilon equal to 0.1 and delta equal to 10 to the minus 2, and another mechanism satisfies maybe 1714 and delta equal to 10 to the minus 10. Which mechanism has better privacy? We believe this depends on the application scenario. It's very hard to say which one is more private. So we propose the privacy spectrum to capture all the most interesting and incomparable epsilon delta. So intuitively, privacy spectrum is the function of the epsilon. So delta of the epsilon is the smallest delta achievable by epsilon. We will plot the privacy spectrum of the Gaussian and Laplacian mechanism to give an intuition. So here, we assume the global sensitivity using the Gaussian and Laplacian mechanism is 1. And then the blue curve is the privacy spectrum of the Laplacian, and the right curve is the privacy spectrum of the Gaussian. To take a closer look, we can see that in most of the privacy region, that epsilon between epsilon equal to 0.2 and epsilon equal to 1. In most of such regions, Gaussian mechanism has much better privacy. But in the region very close to the 1, Laplacian mechanism behaves better because Laplacian can achieve the pure dp. That is, the it can achieve delta equal to 0 cases. But this still already gives us an interesting observation that the probability spectrum give us the full information to compare different mechanisms. Typically, people believe Laplacian is the better mechanism than Gaussian because it can achieve the pure dp. So now that we have set up the motivation, we will move on to the next topic about our problem statement. Our problem statement is the following. Given a mechanism M, we want an efficient algorithm A outputting a good estimate of M's probability spectrum. Here, what we mean efficiency is that the A is the polynomial time algorithm. So there are three desired properties we want the algorithm A has. So first, A shall only black box accept the tested mechanism M. This is to capture the scenario that we want a domain expert with no privacy knowledge can empirically estimate their mechanism themselves. And ideally, we want to make no assumption on the mechanism, but unfortunately, this is not achievable. So we consider the next best thing we can achieve, that is to have a minimal assumption on them. Here, the minimal assumption would typically refer to that the mechanism's output distribution has the density. We shall note that this is a common assumption in this line of work. And then the third desired property is that we want the algorithm A give a tight estimate of the dp spectrum. But unfortunately, this is not achievable. Please refer to our theorem 3 for a formal description, but intuitively, this is due to an observation that a mechanism might have infinite number of neighboring input pairs. So to circumvent such impossibility, we propose the relaxed notion of dp. We call it relative dp. The only difference between relative dp and dp is that instead of considering all the neighboring input in the mechanism's input domain, the relative dp only considers the neighboring input from a chosen set T. This captures the reality that the domain expert may only have several datasets by hand, and he might just want to empirically estimate the privacy of private publication in this dataset. We should also note that relative dp doesn't weight the privacy we obtained from the dp. It provides a global deniability. It's like it provides a deniability for every record in the record universe. And now we are asking, can we compute the relative dp spectrum? Unfortunately, it's still not achievable, so we do the next best thing we can achieve. That is to have a tight estimate of the relative dp spectrum. So here, tight estimate, we mean that the efficient algorithm A shall with high probability give us the tight estimate, the estimate which is alpha close to the true value. Alpha close captures the difference between the estimate and the true value. So to summarize, we want the efficient algorithm A, which only accepts the mechanism in a black box way. It only assumes a minimal assumption on M. It provides a test estimate of the relative dp. We also compare our result with the previous work. So, in contrast of some work, which require more information of the mechanism, our result only require black box access, so which is most suitable for the non-private expert. And we require only a minimal assumption on the M. We don't make an assumption on the mechanism's output space. That means like our estimators can empirically estimate the mechanism with a large output space. And our estimator provides a tight estimate of the privacy. This is to compare with the line of work, we call it DP auditing. So the DP auditing only provides the lower bound of the privacy spectrum. This task is particularly useful if we want to find a buggy implementation or declaim a faulty DP statement. But DP auditing is not that helpful for answering how private a mechanism is. Say, a DP auditing algorithm claims that a mechanism doesn't satisfy epsilon equal to 1 and delta equal to 10 to the minus 10 dp. This result doesn't say that how private the mechanism actually is. It can be the case if like the mechanism is epsilon equal to 1 and delta equal to 1 dp. So our relative dp estimation provides a more useful result. It supports a more wider class of tasks. Since already introduced our problem statement, I would like to shift the gear to the main techniques that help us to achieve to solve the problem. Our main idea is to reduce the privacy estimation problem to binary classification problem. So we first write it down the relative DP privacy spectrums expressions. So on the right-hand side of the expressions, we can break it down into two parts. So in the inner part, the delta subscript M of D and M of D prime. We call it indistinguishability spectrum. Intuitively, it captures the indistinguishability difficulties between a pair of distributions. Here is M of D and M of D prime. And the outside part, the maximal operations, find the worst neighboring input pair, which has the largest indistinguishability spectrum. So our main observation is that the problem of if there's the algorithm that can compute the indistinguishability spectrum, this algorithm will also be the best algorithm for solving a specific binary classification problem P. Of course, the problem P is carefully designed out of the pair of distribution we want to distinguish. More specifically, this pair of the problem P looks like following. So it first uniformly at random pick one of the distribution from x bracket epsilon and y. I will explain later what the x bracket epsilon looks like. And then after choosing a distribution uniformly at random, it will randomly sample a point according to this distribution. And then the problem P asks what the rth label is. So our Eureka moment is to show the link that the algorithm that can compute indistinguishability spectrum will be the best algorithm for solving this specific binary classification problem P. We chopped it down our main series and present an informal version here. Basically, it says that let P be the Bayesian binary classification problem. That's the one we described in the figure before. And let A star be the optimal Bayes classifier for P. That is how we formally capture the best algorithm for solving problem P. And R of A star is the risk of the A star. That is the arrow of for the classifier H for solving the problem P. Then computing the indistinguishability spectrum is equivalent to computing the risk of the H of star. Now we will give an overview of how to prove this theorem. Basically, it has three steps. First, we will show that computing the indistinguishability is equivalent to computing the statistical distance between two random variables, u and v. Of course, here u and v are carefully constructed from the x and y. And then the second step will show that computing the statistical distance between u and v is equivalent to computing the risk of the optimal Bayes classifier H star. Recall how we defined the H star in the previous slide. And then the third step is to put everything together and showing that computing the indistinguishability spectrum is equivalent to computing the risk of the optimal Bayes classifier. Now we will provide more details of the proof. So first, for the first step, we write it down the expression of the indistinguishability spectrum, and we especially take a careful look at the part in the right bounding box. It's quite similar to the statistical distance, but the first term, it is not the density of a random variable. This is because, like, if we're summing up the density of the first term, it will not be 1. So we construct a random variable x bracket epsilon, which is the mixture of two random variables. So with probability 1 to the minus epsilon, it will output the x. With probability 1 minus e to the minus epsilon, it will output the bottom. So we write it down the expression of the statistical distance between x bracketed epsilon and y. And you can see that in the second step, the expression in the below part right bounding box is exactly the same as the part in the upper right bounding box. So this gives us the connection to link the indistinguishability spectrum and the statistical distance of this pair of distribution. So by arrangement, we have the following equation. This equation says that computing the indistinguishability spectrum is equivalent to computing the statistical distance of this pair of the random variables. So now we'll take a closer look at the second step, that computing the statistical distance of this pair of the random variables is equivalent to computing the risk of the Bayes optimal classifier. This is directly from a folklore lemma listed below. And putting all together, we got our series. Now that we have shown the link, our next step is to show how to use this link to construct our estimator framework. So basically, we have the following two observations. First, any binary classifier uses the privacy estimators. These estimators may not have a good accuracy guarantees, like how good the estimator is, but it always can serve as the lower bound. It can output the lower bound of the privacy spectrum. So this means any binary classifier can be used in the DP auditing task. But maybe some of them doesn't have a good performance, of course. And our second observation is that good universe classifiers use the good privacy estimators. This is some classifier which risks convergence to the optimal classifier can turn into estimators which have the tight bound. That's the one we desire. So here we list the relative DP estimation framework, which convert the binary classifier to estimators. So in a high level, for every neighboring input pair, it uses our link to compute an estimate of the indistinguishability spectrum, and then return the maximum over them as the estimate of the privacy spectrum. We later construct an instantiation of our framework using the KN classifier and show that the KN classifier satisfies all the desired properties that we want. So please check our papers for the more formal description and proof. Lastly, we also did some evaluation to show that the empirical estimates generated by our estimators tightly match the analytical result. That's the analytical privacy claim. So we tapped on the building blocks of the DP mechanism, the Laplacian mechanism and the Gaussian mechanism. We also tapped on a more complex classic machine learning task, like random projection and the approximate least square algorithm. All these results show that our empirical estimates tightly match the analogical result. And then we also show that you can use our estimator to complete the DP auditing task, and it can pass the standard test using the DP auditing settings. And that's all I want to share. Thank you very much.